you should receive a kind of a warning message. All right. Hello, everyone. Welcome to the DB database internals meetup. And I'm your today's host, Masaka. And today we are going to cover the chapter 1 of this book, and it's titled Introduction and Overview. Before we begin, let me just emphasize that we have a very strict policy against harassment activities. In SPLVM, we want to encourage everyone to be openly exchanging ideas, either during the meetup or just send chats in the Slack group. But we will monitor and kind of moderate the chat messages and to prevent any potential harassment activities. If you don't know what I'm talking about, just go check out this link, which is linking to an official policy against harassment in ACM activities. Just want to say a few words about myself. I go by Masaka, and I have a Twitter account and that uses my Chinese name, Jia Xiaozhou. So it's a little bit hard to find me. I'm a software engineer at Microsoft, and I'm currently working on open source upstream tools like Kubernetes. I'm using programming languages like Go, Rust, and WebAssembly. I graduated from University of California, San Diego, and while I was in college, I spent almost like 2.5 years working on kind of programming language theory, and I was a huge nerd in programming languages. After I went into the industry, I was still kind of into programming languages, but not as passionate as before, but I still call myself an enthusiast. I co-organized the System and Programming Language Virtual Meetup. We have a co-organizer, Verity Chu. She's a software engineer at AWS RDS, and she graduated from the Australian National University. She has a very strong passion in distributed systems, database internals, and kayaking. So here is how we organize this meetup. We were rotating every week to give an overview of the chapter of the book. And so this week will be me hosting the event, and next week will be Verity. I want to say a few words why you should join the SPLVM. We are kind of a very neat, small community that dedicated to learn computer system concepts by working through the papers, the courses, and the books together. And currently we have 2 meetups ongoing. The first one is so-called database meetup, and that's start in September last year. And we are focusing on learning a college course from Carnegie Mellon University. And that course focuses on the introduction to database management system. And in the second meetup, which is this one, we call it DB internals, and this one will be purely in English, while the previous one is in Chinese. And we'll be working through the database internals book together. And the ultimate goal or the ends of the community is to understand the fundamentals, algorithms, and different trade-offs of real-world system designs. And by system, it's a pretty overused term. What I mean is the distributed systems or database systems or any other data-intensive system. So here is the plan that we laid out last year, and we just finished distributed systems last year, and we started diving into the details of database systems. And hopefully this meetup will be a great starting point for those of you who are not familiar with how database system works. And if you are pretty familiar with database systems, or you are working with databases on a daily job, hopefully this meetup will give you more kind of fundamental knowledge, reaffirm some of the fundamental knowledge about database systems. And particularly, I have an ask for you, those senior folks, just try helping out in this meetup. Whenever either me or the audience have questions we can't figure out and you are pretty experienced, please try to help us. Just say a few words about the meetup itself. We'll be holding the meetup every week on Wednesday, virtually on Zoom. And I will give a approximately 30 minutes presentation and another 30 minutes for the discussion afterwards. All of the meetups will be recorded and the recordings will be uploaded to YouTube. As I said before, they will be unlisted. And we have weekly notes, paper notes, Q&A, and presentation slides are all available free to all. And just check out the GitHub repo. And that's it for all of the administrative details. And before I begin, do you have any questions regarding this? You can either just spell in the chat or you can unmute yourself and ask me directly.
Could I ask you a question?
Sure.
Oh, thank you. So I see on your previous slides that you also have a distributed system meetup. Is that already, does that already happen or it will be in the future?
Yeah, that's a great question. The phase 1 distributed systems and the designing data intensive application meetup have already ended. So we held this meetup last year and it successfully finished.
I see. One follow-up question. So is that for that meetup, is the video also available?
Yeah. All of the videos are online on YouTube. If you can't find them, just DM me in the Slack. I will just give you a link to it. And by the way, for those of you who are English speaker only, the phase 1 distributed systems as well as the database meetup are all in Chinese. So it might be impossible to understand, but all of the materials, including the presentation slides, are written in English. So maybe that will help a little bit.
I see. Thank you. Yeah.
No problem. Oh, by the way, I have seen some issues around the time zone of this meetup. I know 4 p.m. in the Pacific time was not ideal because most of you are still, so this time is in the working hour. I'm open to a time change for the next week. I guess I will just do a poll in the Slack group and see which time slot gets the most votes, and we'll just go with that. Does it sound okay?
I have a question.
Yeah.
So what Slack group should anybody who is not there on the Slack, how can they join the Slack group?
Oh, that's a good question. I will send a link to the chat. Yes, now you can click the link and be able to join the Slack group.
Thank you.
No
And
problem.
yeah, the change of time, yes, we are open. Like at least as far as I am concerned, yes, I am open for the change of time.
Yeah. It's really hard to find a time that works for the European time zone, China and Australia and North America. I will try my best to find a better time slot for this meetup. All right. If we don't have any questions, let's get started. So this is a table of contents for chapter 1, introduction and the overview of database internals. And this is a pretty interesting opening chapter, and because it compares different paradigms of database management systems. Like in here, we have memory versus disk, we have column versus row-oriented DBMS, or the data files versus index files. And all of those comparisons are very interesting to know, and very insightful for you to choose your own database if your team wants to build up a new one. So we'll be learning all of them in today's meetup. Before we begin, let me just kind of clarify what's the difference between database and database management system. You can think of database as a piece of software that provide APIs for retrieval and updating data in disk and memory. But database management system is more than that. We need to admin the database itself. We need to update the database itself. So we need a bunch of components that is outside of the scope of the database, and they kind of bundle together and being shipped as one product. So think about MySQL or early days, the Microsoft SQL Server. They are pretty big products and shipped to the customer with every tools bundled together. And a little bit about the history. In 1970, Ted Codd proposed a new data model, and he calls it the relational model that really defines how we view the data in databases and how we relate them to one another. So he has a paper basically defines three important things for relational model: the structure, integrity, and how do we manipulate the values inside of the relational model. There are a bunch of more data models in the late 2000s, and that with the emergence of the NoSQL movement. We have key value store, graph store, document store, and column family store. And I will talk about the column family a little bit more later. So what is a database? I'm using two quotes from, the first quote is from a influential textbook called Database System Concepts. And it says, a database contains a collection of interrelated data that models the real world. And what does that mean? Think of you have, you want to create a database for university. You have teachers table, students table, and course table. And all of those tables are interconnected or interdependent on each other. For example, the course might have a foreign key to the teacher's table and a foreign key to the student's table. And that's a database job to make those data durable and be available to access by everyone. Not everyone, maybe a controlled group. The second quote is from the database internals. I think it's in the preface and says, the primary job of any database management system is reliably storing data and making it available for users. And this is really talking about two things: durability and availability. There are some interesting evolutions of the paradigms of databases. In the early days, we've seen 1970 with the invention of the relational databases, or later they call it SQL databases. They rely on relational tables and schemas a lot. And all of those mature products like MySQL and Microsoft SQL Server, all of them provide ACID transactions. By ACID, I mean atomicity, consistency, isolation, and durability. Traditionally, they were designed to be able to scale up, but not scale out. So the difference is that scaling up, meaning you are able to change, upgrading from one machine to another. So maybe adding more memory or adding more CPU cores into the machine. Scaling out means that you are adding more nodes into your system. Maybe you want to replicate the data to multiple machines, or you want to shards your data to different partitions. So traditionally, those SQL databases are not designed to be scaled out. So they have a scalability issue at the very beginning. But those SQL databases are very universal in adoption, and they're still serving on those most critical business components today. So entering 2000s, with the emergence of the internet, and the internet companies once has like so-called the internet scale data. They have tons of data, and they want their databases to be always available and to be write intensive and to be highly scalable. So that's why they choose the NoSQL databases. And it is by default horizontal scaling. It's very high performant in writes and massively scalable. And it can even geo-distribute to around the globe. And inspired by the Amazon Dynamo paper, some of the NoSQL databases are by default eventually consistent. If you are not familiar with the consistency levels, you can think of eventual consistent to be, you can understand eventual consistent in this scenario. Think about when your system stop accepting write requests for a while, and eventually your system will have a stable state. So whenever you read a key, you'll always get the latest value after you pass the write for a while. But how long will that take? No one knows because it's eventual. In the last 10 years, I think there is a new paradigm emerges, and they call it the new SQL databases. And it's really a combination of SQL database and NoSQL databases. It has ACID transactions. People just find out transactions are a very good abstraction to simplify their application development. So in those last 10 years, the demands for transactions in those internet databases are increasing. New SQL databases are also horizontal scaling, and they have a tunable consistency levels, and they have SQL support. Some of the examples for each of those paradigms, the first SQL database, I can think of MySQL, Microsoft SQL Server. The second paradigm, NoSQL, I can think of Cassandra, DynamoDB, MongoDB, and NoSQL has Google Spanner, TiDB, CockroachDB, and maybe UtahDB are in this category. All right, so next, the book exposes some of the internal components inside of database, and it just quickly mentioned what they are, but not going into the details. I think we'll learn more about those individual components in the later chapters. So every single database, you can have four components. The first one is a transport layer. The main purpose of this one is to accept requests and return responses. The second component is called the query processor. So the transport layer forwards the requests to the query processor, which parses and optimizes and return the result to the execution engine. Execution engine knows how to carry out the operations either to multiple nodes or to its local single node. And they calls the API provided by the storage engine underlying. The storage engine is responsible for storing, retrieving, managing data in disks and memory. And you can see the right side picture, it has actually more components than what I described here. It has a transaction manager, a log manager, and access methods. We can talk about them later. But to check your basic understanding of this diagram, I have prepared some straightforward questions. So the first question is, can someone explain maybe in a sentence or two, what's an execution plan and who generates it? And when I ask who, I'm referring to which component on the right side picture that generates the execution plan. Does anyone want to give a try?
I'm going to guess that it's the execution engine.
the execution engine generates the execution plan. I think
No, I don't
it's
think so.
higher than that.
May I?
Sorry, I can't hear you.
May I? I believe it's a query optimizer. The query optimizer optimizes the query, writes it as necessary, and then forwards the result to the execution engine. The
Okay.
only thing that the execution engine does is just execute whatever is given.
Okay, so that makes sense. So you're saying the query processor generates the execution plan, and that's being carried out by the execution engine to execute it in the runtime. I will accept that. Does anyone want to explain what an execution plan is?
Well, may I again?
Yeah.
The execution plan is a particular sequence of operators that need to be performed in order to query to run. This is not necessarily the same query that is submitted to query processor. The query processor acts as, well, it's similar to a compiler. It rewrites the query in terms of the fundamental operators.
That's great. That's perfect. So an execution plan is generated by the query processor, and it's a sequence of operators that need to be executed. I have another angle of looking at this definition. I think query execution plan is very similar to abstract syntax tree and in the concept of compilers. You know, compiler look at your source file and generates a AST. I think execution plan, it's query processor look at the queries and generate a graphic representation of the operations. Great. The next question, what components are responsible for concurrency control? And I mean the transaction concurrency control here. Does anyone want to give a try?
I'm going to guess again that it's happening at the transport layer.
It's not happening in the transport layer. The transport only forwards the request to the query processor.
Could I try to answer?
Sure.
Or try to guess? So I think it should be the transaction manager and the lock manager, because to manage the concurrence access, the way there's one implementation, I remember it should be the lock, and another one is use multiple version. We can call it optimistic lock or pessimistic lock. So the transaction manager should make sure your atomic and consistency, and also to be done with some redo log, undo log, and the log manager should help you to control the multi. I could say multi instance to access the same row of data or same block of data.
Okay, yeah, that's great. I think the answer is transaction manager plus the lock manager. Thank you. Serge, I have to ask you to mute yourself because it's a bit noisy in the background. Thank you. Yeah, so just let me repeat what he just said. Transaction manager is responsible for ensuring the atomicity, consistency, isolation, and durability. Maybe not durability. I think the first three parts of the asset for transactions. And the lock manager is responsible for locking the transactions when the database is running it. So together they form the concurrency control in the database system. The third question, can someone answer who is responsible for caching data in memory?
Well, technically it's the buffer manager because
Yes.
buffer is the cache.
Yes, that's a little bit obvious, right? The buffer manager is responsible for caching data in memory. And basically how it works is that whenever you try to retrieve some data, the database first go into a index, either it's a primary index or secondary index. And the index is going to have a reference to the data file in the heap file. And if the data is not in memory, it will tell buffer manager to load the data from disk into memory so that the next time you retrieve the same data, you can just use the memory, not from the disk anymore. And the buffer manager is also responsible for replacer. So if your memory is full and you want to load something into your memory, you have to evict some part of the previous data out into the disk. So that replacer can either be an list recently used or list frequently used replacers. I think this book will go into the details of buffer manager later. So let me just pause here. The author made a very clear statement that whenever we choose databases, we have to be very educated and clear, or I guess, put some efforts into comparing databases. So you don't want to just read the description of the database and it sounds very cool and starts to use it. But you have to first define a goal, like what's the goal, what's the business goal of my current work? And you want to simulate your workloads against different types of DBMS and measure the metrics that are important to you. There are a bunch of benchmarks that you can compare different databases. I think there is a HammerDB, a SimBench. There is also a TPCC, but I don't know too much details about them. If anyone here is very familiar with benchmarking databases, you can jump on and speak for more details. Anyways, and once you simulate the workloads and get results, you want to compare them, and then eventually we can choose the right databases. So that ultimately leads to the purpose of reading this book. I think Alex gave a pretty clear goal for why we are reading this book, and I'm just quoting him. Reading this book should make you well equipped to work productively with these resources and give you a solid understanding of the existing alternatives to concepts described there. And I think the sources and there refer to the academic papers, blogs, textbooks in databases. So it should really serve as an introduction to this huge field and make you very comfortable on reading further topics, maybe some academic papers. All right, let's dive into the chapter 1, and we are going to compare the memory versus disk, column versus row, what is a white column store, and what's the difference between a data file and index file. And finally, I want to touch on buffering, immutability, and ordering properties of the databases. Before we begin, we have some messages in the chat. Let me just read them. Thank you, Serge, for answering the questions in the chat. Yeah, the buffer manager is similar to a page cache. All right, so let me continue. The major reasons we are talking about the difference between memory and disk are those three things, I would say. The first thing is the access time. memory is always faster than disks. And even if you are using solid state drive, and the time difference is 1,000 times. The second difference is that memory, it's much more user-friendly to access. For disk, you have to load a whole page from the disk, and that usually to be 4 kilobytes. And then you are able to find some bytes in that whole page or whole block. But in memory, you can just point to some address in the memory and start reading from there. So it's much simpler reading something in memory. And the third difference is that the disk is non-volatile, but memory is volatile. And what I mean this is whenever you turn off the power for memory, everything you store in memory will be gone, will be wiped out. And we restart your computer and the previous data is just not there. So if you want to make your database durable, you need to use some part of the disks to help you to achieve durability. So in-memory databases store data in memory, and they use disk for recovery and logging. Disk-based DBMS stores data on disk, and they use memory for caching. So you can see both of them are taking advantage of the disk and the memory, but for different purposes. People who use in-memory DBMS are mainly for its performance, and it's much easier to program with memory, and they have much higher granularity. They have granular access to the memory. And people who are using disk-based DBMS, mainly for its durability and lower price. So you have tons of data in your data center. It might be more, it makes more sense to use disks. So as I said, memory is volatile, and anything stored on memory will be wiped out if you have a power off. How can we make in-memory database durable? They use a thing called sequential log file, or which is kind of a append-only thing for storing data. And they also call it the write-ahead log, WAL. And whenever a write request comes into the database, it has to log that thing or log something related to that into the file system in disk before it can return a success to the client. And over time, this log becomes super long, right? You have so many changes coming in. So you want to have kind of a child process that keeps reading the data from the database and then write them into a backup copy. And this backup also is called a checkpoint that basically keeps a version or snapshot of the database for a specific time range. And whenever you lose the data from your database because of a power outage, you can recover your database by loading the last checkpoint and replay from the tail of the log to bring the database into a consistent state. All right, so the second comparison we want to do is the column versus row-oriented DBMS. And here I'm just screenshot two examples here, one for the row-oriented DBMS and another one for column-oriented. Row-oriented databases are pretty common, I would say, and pretty easy to understand. You store all the records in row, and you retrieve them by primary key or by your secondary indexes. For column-oriented DBMS, the data representation is a little bit unusual. You store every value in the column as a sequential order in the disk. So in this example, we have 3 columns: symbol, date, and price. Every value in the symbol is going to score side by side in the disk. So whenever you just read a whole block from the disk, you can read a bunch of values that are in the same column, and that is much more efficient than reading every single records or rows and then just try to get the first column out of it. And another difference you can see here is every single value has a key, which is I believe is a primary key and automatically generated. So if you look at the DAO, they have 1 in front of it and 2. So it keeps incrementing. And those keys are being used to identify the value, which row the value belongs to. And so that's the basic data representations. We can discuss the pros and cons and what scenarios should we use column versus row-oriented databases. The row-oriented databases are a great fit if you want to do like point queries or range scans. If you have a, say, ID 50, I just want to get the record for ID 50, and you can just choose, you can just write a SQL query to select that record by the given ID 50, right? And that would be pretty easy to do in row-oriented DBMS. But if you want to do that in column-oriented DBMS, you have to read a bunch of blocks and one blocks corresponding to one column, and that will be very inefficient. Traditional relational databases like MySQL, PostgreSQL are all row-oriented databases. If you want to do analytical workloads, say your table is super wide, it has 30, 40 columns, and the table is just tremendously big, and it's like 1 terabyte or something. And if you want to read a subset of the columns and want to do some aggregation, column-oriented database is a great fit because all the values from the same column are being stored together, you can do some aggressive optimization on it. You can compress it because you know the data type. For example, it's all just true and false. You can just use 0 and 1 to represent them, and you can compress them using bit masks. That will significantly reduce the size of the value stored in the disk. And over time, people have developed special column-oriented file formats like Apache Parquet and Apache ORC. I don't know about the latter one, but I've heard about Apache Parquet. And there are column-oriented databases like ClickHouse and Apache Kudu. The compression ratio is a very important metric in comparing column-oriented databases, because that, as I said, how you use the compression algorithms will influence the eventual data size in the disk. The next topic is wide column stores. And this is originally inspired by Bigtable. It's a paper published by Google. And the author made a clear distinction that we don't want to confuse us about wide column stores and column-oriented databases. They are not the same thing. Wide column stores, eventually in the disk, they store the data in rows. So it's much like a row-oriented database instead of column-oriented databases. So don't be confused by the name it has. In the book, it says data is represented as a multi-dimensional map. Columns are grouped into column families, and inside each column family, data is stored row-wise. So you can think of the data in the wide column store as two-dimensional dictionaries. You have a key that maps to a list of column families, but in each column family, you have kind of like a table-like data representation. Each record is being stored in row. And this layout is best for storing data retrieved by a key or a sequence of keys. And some of the examples inspired by big tables are Cassandra, HBase, DynamoDB, and Azure Tables. The previous description is a little bit vague. Let's take a look at an example here. On the right side, we have a screenshot for so-called the web table, and that was originally used by Google. They want to store a snapshot of the web contents, and you can see the keys are web URLs, but interestingly, they are reversed. So the first one is www.cnn.com, but in a reversed way. And they have all of those keys. And each key is maps to two column families, contents and anchor. Contents just are a history of the web contents defined by HTML. And anchors are a bunch of links in this page, I believe. So the right side picture is just a data representation. How it's being stored in the disk, it's described in the bottom left picture. And you can see every single column family has its own table. And within each column family, the same row keys or the keys to query are sorted and bundled together. So you can really think of the advantage of doing this way is that we can quickly scan a bunch of keys, in this case, the website URLs, and be able to get a bunch of contents from it. So this is drastically different from the column-oriented databases. Does anyone have any questions regarding this example?
I have a question. So for the wide column stores, what's the advantage of it over the traditional row-based store?
Yeah, that's a good question. I was wondering the same thing when I was reading this, and I couldn't think of a clear advantage except that by nature, wide column stores partition the data based on the column families. So taking the distributed system into consideration, it's easily to program to shards the data than the traditional row-oriented databases. That's one of the advantage I can think of. Does anyone want to add more? Because I'm also curious.
Yeah, could I add a follow-up question? So when you see we can use a column family to do the partition of the data, so it means the different column family will be sharded to the different VM, or what does it mean? So we can use column family to shard in the data.
Each column family is stored as its own table in the disk. So whether it's one column family for one node, or it doesn't matter because they are just defined to be one table. If this table is too big, they will vertically cut this table into different shards.
Okay, I see.
Yep.
May I add a comment?
Sure.
Yeah, so the reason behind the column family versus the row-based or column-based is that you can see the column family is mostly used in the some kind of a big data architecture like Hive, HBase, or Cassandra. So the reason behind it, it's kind of like related to the sharding, but not directly. The reason behind this is that for the OLAP analytics, and usually for a table, there's a lot of columns in the data. Like for example, for the OLTP, usually a table may probably have tens or 20 columns in a table. But for the OLAP systems, a row can have 100 or even 1,000 columns. So to make it efficient, like to query in each row. So that's the reason behind the column family. And also for column family, and because usually the big data storage use key value storage to to store the data. So column family, as you can see, is a tuple-based storage pattern, which is very suitable for the key value-based storage.
Yeah, that's a great answer. Thanks, David. So if I understand correctly, this is a great fit for OLTP workloads. Is that what you said?
No, I mean for the big data analytic, for the big data processing, it's not. I don't think it's for OLTP. It's mainly for the OLAP, like for the data processing, but different from the column-based. It's for some table with 100 or even 1,000 of columns in a single row.
Got you.
And especially for some data warehouse, that there are some structured or semi-structured data type. So it's very suitable for the column family formatted database.
Yeah.
But I think the question is compare the row-based storage with the wide column storage instead of the column-oriented storage. Because I think Mosaka mentioned before that the wide column storage is kind of like a row storage.
Yes, the data in the column family are stored in rows.
So I would assume that the HBase, Cassandra, that wide column storage, they are still suitable for OLTP instead of OLAP, right?
Yeah, I would think so.
Okay, yeah, thanks.
It depends on the processing engine. And for example, to use Cassandra for the OLTP is totally fine. To use HBase for the OLTP, it's not suitable. It's dependent on both the storage format as well as the processing engine.
Got you. Yeah, so it depends on how it's being used, right? I think Serge, do you have a comment?
Yes, I think I have, because I have some experience with these kind of things.
Sure.
So just to clarify, I need to clarify a couple of things, because there was also a question on the forum.
Mm-hmm.
If you have to decide between row first or column first storage, in either case, you can think of it as a two-dimensional structure. Distinguishing between column first and row first is like having a dictionary of dictionaries. And the question is, what goes first? Is it column first and rows inside, or the other way around? That depends on your access pattern. As usual with dictionaries, you organize them, if you have nested dictionaries, in the order which is relevant to your access pattern. Wide column is actually a misnomer. It is a three-dimensional structure. So each cell, row, column, is actually like a small table. So you have index within index within index. Is it suitable for OLTP? Maybe. Why is it useful? Here is why. Suppose you retrieve documents from the web that are huge HTML documents. You parse them and you store them.
Right.
When you parse them, it's a very expensive operation. You want parse results to be available immediately to you. So you parse HTML page, you find all the links. You find all the anchors. You have the document itself, but you store all parsed links separately, right? So how would it look for a single document? You have separate columns. Here are all the links that I found on this page. Here's the page itself, just in case we also need it. Here's the list of all URLs that are found in links. Wait, for one document, you have several anchors. We have several links. So it's like a table inside the table. Why is it useful? You don't want to parse it again. So it's a three-dimensional structure, row, column, but column says what's inside, right? Let's say a column says all anchors. There's more than one. So do you think it's normalized? Well, depends on how you define the key. If your key is a single page, let's say the URL, it's not normalized. But if your key is a composite key because you want to say, I want the page URL plus I want the anchor, then it is normalized, but essentially it's a page within a page. So it's a three-dimensional structure.
Wow,
That's about it.
that's a pretty impressive perspective looking into it. I never thought about that way. So I can think of white column store to be a three-dimensional tables, a table of tables, I guess.
Yeah.
Oh,
So
super
white
table.
column is a misnomer. The white column, the column name is actually a nested table name.
Mhm.
So it's really wide because you have the whole table inside one column. Instead of the usual one value, you have the whole set, right? That's why it's called white column, but the name is really bad.
Yes.
I don't know if I answered this question. Like, I don't know if Christy would agree with me.
I think you made a very, very good point. This is the first time I heard that the white column could be think of as a three-dimensional. I guess the first dimension would be the row key, the second would be the column key, and the third dimension would just be all the content in defined by this row and column key, right?
Right. But also there is another thing that may be four-dimensional. Look at it this way. One more dimension will be a time series, right? You have the same page, but the page might have changed. So you have one record, one nested record per anchor for today,
Mhm.
the different one for yesterday. So you have another dimension, time. And that's actually what is represented in this particular picture on the presentation. See anchor at a different times, let's say T9 or T8. At time T9, there is CNNSI. At previous time T8, something different, a Canadian link, because the page might have changed.
Right.
Yeah. And you might want to
And-
ask a question. Yeah, go ahead, Christy, I'm sorry.
No. I just say I see. It just go ahead.
Yeah. Well,
Yeah,
I'm
it's
sorry
a really
for
interesting pattern here.
I'm sorry for imposing, but I had to do this kind of thing before. That's why.
No, thank you very much. That's a very
Yeah, thank you.
insightful
Yeah.
point.
Yeah. Also, to answer another related question that you asked, you said it's surprising that the URL are presented in the reverse order. That's how pages are organized. That's how pages are organized in the DNS system.
Yeah.
It's opposite of the order in the file system, right? Because the file system, let's say in Windows, starts with partition number. It's drive C or drive D or whatever, right? But the network URLs go backward. You start with com. What do we have under com? Oh, we have 10,000 companies.
Mhm.
And one of them is com.cnn. What do we have under com.cnn.com? Oh, we have www, which is HTML page. We have some JavaScript entry. We have something else, FTP, different servers. So it gets more detail as you progress. So that's why it's stored reversed.
Right, from generic to specific, and it's
right.
sorted. So it makes
sorted.
total sense here.
Actually, if you look at the DNS system, like the DNS is the subsystem, the global system of servers that helps you reserve and resolve those URLs to IP addresses. It starts with 26 or so global servers. You ask them, where is com? Oh, say, all com is here. Go to this server, ask more questions. So you go to the second server and said, I know you're com. Where is com.cnn? Oh, say, CNN is here in Australia, here in America, here in Japan. And you go from there, you just go to more and more specific queries. So that's how actually the internet is organized. So it's not an
Great.
accident. Yep.
Thank you very much, Serge.
No
Do you want to quickly introduce yourself?
Well, I'm a software engineer. I'm a consultant. I live in New York, work mostly for financial companies. I'm independent.
Got you.
I'm not associated with any large company.
Yeah, you're very experienced.
I'm a little bit old, yes.
I have one more question. So for the wide column storage, I think another advantage might be even the user want to change the schema or add or remove the column offline, they don't need to do migration like what role-based storage does. Is that correct?
It might be, not necessarily so, but it can be the case because look at it this way. Suppose you have an anchor wide column in the example below. Do you want to store these anchors for every row in a separate file? You might say, yeah, I want it. Why not? See, one of the interesting thing about wide rows that you often want to see one group at a time. You don't care about any other group. There may be many groups, anchors, URLs, embedded pictures, whatever have you, right? But you're only interested in, let's say, URLs. Why? Let's say you're crawling the web and you want to follow up, let's say, who points here? I go to other URLs and pick up pages from there. This is standard page harvesting, right? So if you do this work, you don't care about every other column, right? You only care about the columns you're interested in, such as anchor, or more specifically, probably link.
Right.
So if your table is huge, as previously was mentioned, you only want one column because you don't need anything else. You would save lots of IO on that. And if you happen to store it in a separate file, you are golden. You simply read from that file. So yes, grouping of columns, column groups, or wide columns equivalently, they are sometimes stored separately, exactly for the same reason as indexes that are stored separately, because sometimes you want to read the indexes, and believe it or not, you don't need to read the table.
Yeah.
That's actually, yeah, go ahead, please.
No. I mean, I just got it.
Excellent.
Great.
Well, I guess that's pretty much it.
Thank
could I
you.
ask a basic
Yeah, sure.
question? So,
Sure.
yeah, so I see in the slide there are in the left that's the two table, in the right that's a that's a JSON file, in my opinion. Then yeah, this is a very basic question. So for the left picture, the left two table that are what big table actually stores, and on the right that's just what the data contains. It has nothing to do with the big table. Big table only use the left part. So
Yes.
also big table basically stores the data. The data on the right, it will store in the format of the left two tables. Okay.
Yes, that's very likely. What do you have on the right? You have a JSON structure, right? So essentially what JSON structure is, it's a dictionary of dictionaries. So that's how indices are organized. So the data is grouped by logic. On the left-hand side is how data may be stored. I actually don't know how it is stored, but what the picture suggests, as Christy noticed, that column families may be stored in separate files because it's more efficient. Because you can only read one of them and you just ignore the rest, right? If you want to have anchors, you don't really care to read the whole document. So why waste IO?
Yep.
Did I answer a question or?
Yeah.
Okay.
Thank you. Yeah.
I'm sorry, I didn't mean to impose. I apologize.
It's okay.
Please go on.
All right. Do we have any more questions?
Yes, I have one question.
Sure.
So for this wide column store, do we still need an index? Like a row base, we always create an index to increase the search. So for this white column, since we already have the column family, do we still need the index?
I guess that's another question for search.
No, it's a common question. Let me answer with a question to a question. Why would we need an index? We want an index because we want to find our one cell faster, right? You use binary search trees or other trees to find it faster. So do you want an index? Only if you want to find it faster. Here is the problem.
I guess your answer to this is yes, we can have
no,
okay.
no, not necessarily. Let's step one, like make one step in. Sometimes index is actually bad for performance. That seems very strange, but that's how it is, because index is a sorted, it's a tree, right? So if you go down the tree, you jump from one place to the other because that's how you go fast, right? But remember, in database, everything is on disk. So you have to do random IO. Random IO is slow. So if your index is already in memory, yeah, it's good. If your index is still on disk, it can be slow. In fact, a very popular and powerful Oracle optimizer tries to estimate the cardinality and says, by my estimate, if you have to read more than 25% of data, don't use the index. Do sequential scan, it will be faster because it's sequential IO. So what Oracle does, it uses a large buffer, not 4K. It uses 32 or 64K, read it into the memory in batch, and then do a linear scan, and it's still faster. Because going from tiny pages on the index and jumping around can be actually very slow. It doesn't have to be in the memory. So the answer is it depends. And the optimizers know how to do that.
But I guess you can create index on the specific columns.
Yes.
Yeah.
But here's the problem. You need to know which columns.
Yeah.
Right? So if somebody uses a query and you use the same query all the time, that's good. You just put an index, you know, it's always going to be used. It's always going to be useful. But if you don't guess right, then it doesn't help. That's actually a favorite interview questions. I used to ask this question. You have a table and you have an index, and the index can be used. Should it be? And the answer is, it depends. If your query materializes more than 25% of data, the answer is, it's just faster to read the whole table until you find it. It's sequential IO in large buffers.
All right. Does it answer your question?
If I understand, it depends. So
yes.
If we read the data based on the column family, we don't need it. Just immediately read all the table.
No, that's a big saving. Because if you look at this table and everything nested in, as it's shown on the right, you might need 1% and you don't really need the rest. So reading it all from the drive is very expensive. You don't need it.
I mean, if you analyze or process those big data, if you directly want to get the all occur, so you just directly read the whole table. You don't need to index it. You can, is that right?
Maybe. It depends on what you want to do. Here's the problem. Your indexing scheme depends on your access path. Unfortunately, there is no universal access path. I want one thing, you might want the other thing. That's why you can have multiple indices. And even multiple indices can be bad. It's a trade-off. Because indices actually slow down performance in some cases, remember? Jumping over small leaves again and again and again, random IO, Also, imagine what would happen if you need to update the table. You have to update the index as well. And if you have 50 indices, because your table is huge, and everybody wants their own path, and you have to have 50 indices, and 50 indices is just too much. I know that in my experience, I had a situation when I had updated table by 12 million rows in a single operation. That's a lot. So what I would do is just, I remove the index first. I import all the data and say, create me a new index. It's cheaper than to update through the index because lots of random small IOs. The difference is really significant. Maybe the difference between 10 minutes to update and 3 hours to update.
Yeah, I guess there are just too many, I guess, trade-offs in here, and we can't agree on a very scientific answer to all of those questions, and really depends on specific scenarios what we are talking about here. All right, I'd like to move on because we have some great discussions here, and I don't want to make this meetup to overtime. Let me move on, and after I finish, if we still have questions regarding the white column stores, we can jump back to here to discuss more, or even better, I haven't, to be honest, I haven't read the big table paper. Maybe we can have an offsite meetup to just read that paper and discuss it again, so we have more context on what white column store really is. All right, so the third comparison is the data versus index files. And here I have a question for all of you. Why do we need a database management system and not just a bunch of files or flat files provided by the OS file system? Why can't we just implement the data files using operating system file system instead of, DBMS doing its own, doing the same thing twice? Does anyone have any thoughts? Actually kind of give some hints to this question. So the book listed 3 things: storage efficiency, access efficiency, and update efficiency. And I think my understanding is that when the database stores the data into the files, they have its own unique encodings to those data files because they want to make the retrieval and the update to these files more efficient. So the operating system doesn't know how those data represent what's the distribution of those data. They only know how to read and write from the disk to the memory. So in this case, it might make more sense for the database management system to implement its own file retrieval mechanism so that they can maximize the efficiency of the access patterns. And moving on, so when we are saying data files, we mean those files that store the DACA records or those tuples. Either can be row-oriented or column-oriented, it doesn't matter. And those data files have different file layouts, depends on what kind of database you are using. But usually all of the file is going to be partitioned into pages or blocks, and each page is about 4 kilobytes. In the book, author summarized there are 3 major file layouts. The first one is the index organized tables. So basically you store everything into the index itself. And the second file layout is called the heap files. And this one is pretty common in the relational database. You store the record without any order. Maybe just whenever you write something, you just store it to the latest offset of the heap files. And the third option is the hashed files. So whenever you sort something, you hash it, and then it goes to that hashed key corresponding block in the disk. And in each file, they have a bunch of blocks or pages, and we can impose different page layout to organize those pages. And I think the most common used one is called the slotted pages. And basically the high level idea for this one is think about a page as like a square or rectangle, and you allocate empty spaces into the upcoming records. And for each record, you maintain some metadata to reference where the record starts in the page. So I can first go to the metadata to get the offset, and then I go to the offset to get the real tuple in that page. And this thing is called slotted pages. I think the book will go into details of how this is implemented later. All right, to the contrast, we have index files. Those index files are storing the metadata of the data, and they remap to the location of the data files. We have two kinds of indexes. We have primary index and secondary index. The primary index is an index on the primary key, and most likely it's built in whenever you create a table, define which column is primary key, and you have a primary index. And this primary index is used to retrieve the records in your table. We can have a user-defined secondary indices, and usually if you are using SQL to define, you can do like create index to create secondary indices. And there are two ways in database design of where can we store the value to secondary indices. The first idea is that the value to the index could just be the actual record. And the second approach is storing a reference or a pointer to the data file. And you can see how if you have read-intensive scenario or write-intensive scenario, how these two have pros and cons. So if you are read-intensive, having the value in the index would be more efficient. If you are write-intensive, you change the data file and all the index reference in it will automatically update. So that would be more efficient. And there is another term called the cluster index. So to reduce the actual disk access whenever if you are using like a B tree for index, you go to the bottom of the B tree, you find the leaf node, and you then have a pointer to the data file to retrieve that block. To reduce this extra step to find the data file, cluster index will store the records in a sorting order that is matching what the index has. So for example, I screenshot two diagrams from the book. One is the index organized table. You can see those records are stored within the leaf node, and it's being sorted automatically if you're using a B+ tree. And the second is an index file, and each leaf node is pointing to somewhere in the data file to retrieve that data. And I searched for MySQL, and it says that MySQL InnoDB actually always do cluster index for primary key. So everything you insert into MySQL tables, they will automatically sort it according to the primary key. And there is more things towards primary index and secondary index. And this is called the primary index as an indirection. And authors said this is pretty debatable and controversial. So there is no agreement on which one's better. I guess it depends on scenarios. So the diagram on the left says that the secondary index points to the data file directly. And the second diagram on the right says that the secondary index always points to the primary index. So think about again, if you have read intensive or write intensive scenarios, if you have read intensive, the left diagram makes more sense. Your secondary index go directly into the data file and fetch the data for you without an extra step going into the primary index and then do another random IO to the data files. But if you are write intensive, then maybe the right diagram makes more sense. You update the data in the data file and it update the primary index, then you don't need to update the secondary indices because they automatically point to the right location by the direction given by the primary index. And the last part, I guess, is a pretty vague description. It says that every single database we are comparing here today have something in common, whether they are using buffering, using immutability, or orderings. And while we are comparing databases, we can think of whether buffering, immutability, and ordering really matters or not in our scenarios. So buffering here means that we buffer the disks, the blocks into the memory. And most databases do this in the buffer pool. And there are also databases that try to avoid buffering. Immutability means that whenever you have data written into the data files, and can you do a random update to the data file, or it's append only, you can only append new data into it. And ordering is obviously saying that your data is sorted by some order or not. And that's also worth considering. I guess we can come back to the three major stuff when we are diving into the B tree and further topics in the later of this book. But this is a pretty interesting observation that every single database has these three things in common. All right, that's it for my overview. I originally thought it would take about 40 minutes, but since we have some questions in the middle and it takes almost takes almost an hour and 20 minutes. Do we have any questions on the later part of the presentation?
Could we go back to the first page for the data versus index?
Yes. This one?
Yeah, this one. Yeah. So yeah, I could you explain the point A again? Sorry, I might miss that, but I didn't understand the point A. It's 1, 2, 3. They are three kinds of choice, or they are
So the data files can be implemented as those either one of those three categories: index organized tables, heap files, or hash files. And as I said, heap files are those like random position records. When you write them in, they doesn't have a specific order. Hash files records are stored in those little buckets, and each bucket has a hash ID. Whenever you hash the key, it goes into one of the bucket. And when you retrieve them, you can also hash the key you want to retrieve, and that goes to the bucket as well. The index organized tables, it's pretty vaguely described in the textbook, but I think it's pretty similar to clustered index. If I'm wrong, please correct me.
I see.
Yeah. I also have a question on this page. So what do you mean the heap files? Has any relation to the heap structure? I didn't understand.
You can think of random files. That makes more sense, right?
Okay, it's not from the lower address of memory or disk to the higher address. It's just a randomly file. It's a random file. So we can go to from 3, then 5, then 1, right?
Yeah, so it just says that the records are stored without any particular order.
Okay, 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 thank you.
No problem. All right, and seems like people are very interested in the big table white column stores, and I think I apologize that I didn't read this paper, so I can't answer some of the questions we have in here. If people are very interested, I can find some time to read this paper together, and we can discuss some of the details in this paper. How does it sound? Maybe we can find some time later this week or next week to do the discussions.
Sounds good to me.
All right.
Yeah, I want to just add one point. I just thought about to the page 25. So the pros and the cons for the white column store. So I don't remember if Serge mentioned that. So one pro I think for the white column stores is for the JSON file, it only has 2 layers. The depth is 2, right? Or 3, you can say. We have bracket within bracket. So one of the pros for the white column store is we can have very in-depth data stored in for the JSON. Like the JSON currently the depth is only 2. We can have depth for 10, for 20 to store very complicated data. I think that's not doable for traditional SQL. For traditional SQL, we can only at most store an array, right? For a column,
Right.
it can at most be an array. So that's only 1 depth. And if we want to store more complicated data, the only way to do is store a blob using the store blob, serialize the data. But serialized data, you have to serialize and deserialize. It's not very clear what we are storing unless we deserialize that. But for the JSON, for the JSON on the right, we can store every time when we go 1 depth deeper, we will break the table again. We will break it like here. We have depth of 2. We break it into. We have break into all the column family. If we want to store more complicated data, on the right, we have object of object of object. This is just some internal, because I also work at Google, and in our internally the database, we define the schema for database. We use the protobuf, and the database, the schema of the database can be very complicated. It can be an object of object of object of object. So the depth can be very deep. So I didn't realize how they are stored, because I know SQL only can store at most an array. Otherwise, they are stored in blob. But after I look at this slide, I realized every time when we go 1 depth deeper, we will break the table in again. So like if we have that's basically what I want to say is we can store very complicated data using this kind of white column stores. So
you actually confuses me now. So what you are saying is in white column store, the JSON on the right can be infinitely nested.
Yeah, right. Yeah, that's basically what I mean. Like if outside like the outside, the most outside is an array of websites. Then we go into the contents. The second depth is contents. The third depth is like contents. We can go into like the paragraphs. And the fourth steps, we can break the paragraph into more like pictures, then words, then something. Yeah, it's like we can store very complicated class object into the table. So outside is the object is school. Then school go within school there are many students. For every student, we have more properties like the height, like the weight. Then and we have the scores. Okay, scores is an array. It's an array. It has the math score, the language English score. You have the physics score. Then you for the math score you have it's another array. The math score is the math score for the grade 1, grade 2 for your high school, for your university score. You can define this kind of very complicated structure. Then how do we store that data in the database? If we use a traditional SQL, only way you do is using the blob. You serialize and deserialize. But using these wide column stores, you can every time when we go one depth deeper, we just break the table again. And if we use this, gives us very flexible query, because if we only store the serialized binary, it's very hard for us to query one field in the serialized object. We want to query just imagine I want to query the math score of a student, and for the university for the first year, first year, that's hard for us to query that field if it's serialized. But internally, if you use Google's query using the big table, it's very easy. We have very good query language to do that. I think that's how the wide column store gives us that power.
Great. Thank you very much for sharing.
Can I chime in a little bit?
Sure, David.
Yeah, so from the big data, that's a paper, the original column family cannot have like so much depth. So based on the paper, in that paper, there are two concepts. One is a column family, and the second is a row family. And they only have like these two hierarchies. So theoretically, the column family cannot nested too much. But in the real usage, we can define different data types like a map, like an array in the row family. So that can have flexibility compared to the traditional RDMS. But the column family itself didn't support this kind of like nested structure. That's the first part. And the second is that for the traditional DBMS, early for the modern like MySQL or Postgres, most of the RDBMS support the JSON format nowadays. Like for example, in Postgres, we can even create an index based on JSON tag, which we can create the gene index, which will index the JSON object based on the field we defined. So yeah, so in fact, you can say most of the RDBMS are tend like to adopt to the JSON or semi-structured data type in nowadays.
Right, that's what I have heard. The biggest DBMS, relational DBMS are adopting JSON data types in columns as well. And as you mentioned that when I first heard the infinitely nested JSON, I was thinking about, was that just like MongoDB or document store? Like, then I was confused. What's the difference between wide column store versus document store? But yeah, you would really clarify that maybe in the original implementation, wide column store cannot have infinite nested layers in column family, which makes sense.
May I add something?
Sure.
So I have some experience with HBase. So I have we have maintained a OpenTXDB on it. So I'd like to share how OpenTXDB uses the wide column model. So usually for TXDB, the row key will be like 1 hour. 1 day is a time range, right? And like the paper said, the qualifier and the cells there could be a lot of cells in one column family, and they basically they are the same type. For example, for the 1 hour data, we will create a qualifier for every minute. And in this case, this column will have like a 60 qualifier, 60 cells. And in HBase, depends on how you implement it, the qualifier and the value are separated actually. So all the qualifier names are serialized into a big binary chunk. So you can do a lot of encoding and compression to it, right? And the value, yeah, and the values could also be, they are actually put together and it could be encoded like you can use in delta encoding or anything, any encoding. So in that way, if you want to get 1 hour's data, you basically get all the qualifier and the values, and that's how the analytical workload works.
Yeah, that makes sense.
Yeah, that's one way to use the Y column. And so if you read the paper, you will notice that the paper said in one column family, there could be a lot of qualifiers, depend on your scenario.
So I can think of qualify as attributes in tables, in relational tables.
Yeah. So so I don't know. So we just mentioned how Google use nested data structure, right? So I have one similar use case that we model the qualifier name. So the name could be nested,
Oh, okay.
Yeah, so different name maps to different field, right? So they are nested and could be any depths. But really it depends on how you're modeling your data, yeah.
Yeah, wow, it's much more versatile than I thought. It's amazing. All right, thank you, Xiaoguang. And now it's a little bit over time, and I think I can stop here. And this is a great start to our first DB internals meetup, and we had some great discussions on those topics. Although I introduced them in a very high level layer, but we went into details, and that's a great thing. I will find some time to read the big table paper. It seems people are interested, and we will see you next week. And we'll read chapter 2 of database internals, and that will be B-tree implementation. And I think Verity will present that. All right, thank you everyone for joining today's meetup. Let me stop the sharing now. And for those of you who have helped answer the questions, Xiaoguang and Chen and David, sorry, I didn't give you a chance to introduce yourself, and I already start the recording. If you don't mind, can you just give a short introduction of yourself so we can know you? And yeah, David, do you want to go first?
Oh yeah, sure. Hi everyone, I'm David. Yeah, and I'm a software engineer for almost 12 years, and most focus on the end-to-end big data product delivery to the end user, including some network topology and big data computing and storage, as well as some machine learning architecture. Yeah, and very glad to having me here and really learn a lot here.
David is one of the most experienced and insightful person I've ever seen in this meetup series, and he's an old member, and definitely I learned a great deal from him. Chan, do you want to introduce?
Oh yeah, thank you. So I'm also a software engineer. I have 5 years of experience. I'm not an expert in infra, but I'm very interested in learning about the database and also other infra. So yeah, and I think this is very meaningful. This meetup is very useful. Yeah, so looking forward to the future meetup. Yeah.
Great.
Thank you.
Thank you. And did I miss anyone? Christy and Xiaoguang.
So I'm a software engineer, around 4 years experience. I basically work in a backend infrastructure team, very similar to AWS, but I'm not in Amazon. We are doing a self-provisioning database. So I very interested in different kind of database, the internal implementation and how to use them to improve the performance. Yeah, I feel this meetup is very great, and I can learn a lot from it. Thank you for hosting.
Thank you very much for joining.
Yeah. So I have like almost 10 years working experience. I build this some database and also I'm working on some machine learning recommendation systems. But I still feel like learning all those stuff. Yeah.
Yeah, that's great. Thank you so much for bringing your, honestly, I was the junior guy here because I only have nearly 2 years of experience. So I will definitely learn from you guys, and you are more experienced. And I'm glad that you all joined the meetup and willing to share. And hopefully I can see you next time. Thank you very much. I'm going to end here. See you.